Here we will investigate the symmetries of a longer cosine modulation function using a Python example. So let's take a modulated analysis filter bank with impulse responses given by this equation. Here, with a cosine modulation function, it's like a DCT4. Then for subband k equals to 0, for n equals to 8 subbands, and for a length of 32, we get this plot here. And we see the symmetries. So we have blocks of 8 samples. This is the block 0. And then we see the block 1 is equal to the block 0, but with inverted sign and flipped from left to right. Then block 2, it will be equals to block 0, but with an inverted sign. And finally, block 3 is just the flipped version from left to right of block 0. So this image visualizes the following symmetry. We have that the second block is identical to flipping and negating the first block. We can see just by the numbers as the same which is described by this picture. The second block is identical to flipping and negating the first block. The third block is identical to negating the first block, and the last block is identical to flipping the first block. And here's the proof of how we're doing, and so on. So we see the following rule: every second block is flipped, and after 2 blocks we get a sign change. This is not only true for the first subband, but also for all other subbands k. To show this, how this is useful for a matrix implementation, let's take the following example. We have a prototype function h of n, and we have n is equal to 4 subbands. Then our modulated impulse response for subband k equals to 0 with the basic DCT4 cosine modulation function is given here. And to show that the basic principle, the time shift of the MDCT was omitted. Now we can implement it with a block size of 4 for a filter length of 8, twice as long as the DCT4. We have 2 modulated blocks with block numbers 0 and 1 with the time reversal for the analysis. So for H0, so we have here H0, block 0 and block 1, and we have here these elements. And you see there's a time reversal for the analysis for H0. Now we can write the modulation with the length 2 times n with our cosine function with the help of a matrix formulation, which includes the flipping and the sign change of the second cosine modulation block. For that, we also define the first block of our cosine modulation function given here. Observe that the T0 transposed is also the first column of our DCT4 matrix. Hence, for the first block of the modulated impulse response, we simply get this here. You see it's diagonal here. And because of the modulation block, block 1, is time flipped and sign changed compared to the first block, block 0, we obtain our second modulated block as given here. So instead of flipping and changing the sign of our modulation vector Tz, we apply the flipping and sign change to the matrix of the prototype function. And we have now this diagonal here, and you see we have this sign changes here, and then we have this equation, and hence we can put both together in the z domain. It's given here. So we have our first block, z to the power of 0. We have our second block, z to the power of -1. And this is what we get here. And observe that we can simply add the 2 previous matrices since they have the same size, and we can factor out the vector of the modulation function T0, and multiply the second block with z to the power of minus 1 to obtain the z transform. So this is what we are doing here. We have this matrix. We're adding this matrix to this one, and this is the result. We also factor out the vector of the modulation t0, and we are multiplying the second block with z to the power of minus 1, and then we have our z transform. We see that we obtain a very compact representation for the modulation, where we separated the prototype function and the modulation function into two different matrices, and the matrix with the prototype function is a sparse matrix. If we extend this example to filters of length of 4 blocks, we would get this cross-shaped matrix. Observe that every polynomial in this resulting matrix is downsampled version of the prototype h of n by a factor of 2 times capital N. In our case, 2 times capital N is equal to 8. In addition, every second resulting value after this downsampling is also sign changed. We can also obtain the sign change by replacing z to the power of 2 by minus z to the power of 2 in the z transform for the 2 times capital N downsampled version. So this matrix times our column vector T0 transposed above results in the polyphase representation of our subband filter H0 and for the subband k equals to 0. So this is the first of the 4 filters we have in our modulated filter bank. We obtain all 4 filters if we just use the complete DCT4 transform matrix T given here. So for instance, with n equals to 4, we get for t these values here using this Python function. We are just implementing this in Python. Fortunately, we obtain the same symmetries for the first subband, also for the higher subbands. In summary, we have an analysis filter bank with the impulse response given here, and its analysis polyphase matrix H of C can be written as a multiplication of a sparse cross-shaped matrix with a DCT4 transform matrix T given here. And notice that for odd numbers of subbands n, we would obtain one value or one polynomial in the center of the matrix.